case 4. Both capacity and load are random processes, but they are stationary in nature, and we would like to find how to estimate the random time to failure in such a situation and estimate the reliability function, hazard function, etc. So let's go back to the definition of an overload type failure. So we discussed that the safety margin is not a monotonic function of time, and failure occurs as soon as the margin function, the safety margin, goes out of the safe set during any time in the reference interval. And the first instance that it happens, we have the time to failure, which is a random variable. So the reliability function is the probability that the safety margin stays in the safe set at all times between 0 and t. So let us say the safety margin is the difference of the capacity process and the demand process, and in such a case, or if we are able to write it in any other manner, maybe an implicit function, that the safety margin becoming negative is equivalent to failure. So in this setup, anytime the safety margin becomes negative, we have failure, and the first instance that happens is our time to failure. So we'll see that if we have a stationary process, then this would be equivalent to finding the rate at which the margin process M crosses the 0 barrier. So it was in the safe set above the barrier of 0, and as soon as it falls below 0, we have failure, and the first time it happens, we have that's a random time to failure. So if you know the rate at which this margin process crosses that barrier of 0, we would be able to, under certain assumptions, estimate the time to failure, the reliability function, and so on. So we have been talking about process, stationarity, all of this, but we haven't defined them formally yet. So let's spend the next few slides covering these preliminaries. So a stochastic process, a random process, a random function can be thought of as a function of time, let us say time, which behaves in a kind of uncertain manner. If we have to define it formally, then a random process is a family of random variables indexed by t from an index set capital T, and these random variables together define the random process. And you can imagine that these random variables at different times would most likely be dependent, unless we are talking about a process like a pure white noise, then it's independent at all times. But in general, we have at any particular value of the index t, let us say t1, x of t1, we can call it x1, and that x1 is a random variable, and a particular realization of that random variable is, let us say, little x t1. So likewise, we can define x t2 and so on for all values of the index set. So we can also interpret that if we do this again and again, if we get realizations of xt for all possible values of t, so what we would have is called an ensemble of the ensemble of sample functions of the stochastic process. Now, because these x's are all random variables, and depending on the size of the index set capital T, we would need to know the joint probability description of all these random variables, xt1, xt2, up to xtn. So to fully define a stochastic process, we would need the joint density function or distribution function of all orders, depending on what the size of my index set is. Now, later we are going to talk about a Gaussian process. So a process is Gaussian if its joint density of all those x's that we talked about, joint density of any order is multivariate normal. So that defines a Gaussian process. Now let us define a few more quantities. So the mean value function, if we fix the value of t, we are left with random variable x of t, and we know how to find its expectation. We just integrate x fx dx over the entire range minus infinity to plus infinity. So that would give me the mean value at particular t, and if I can do it at all possible times, I have the mean value function. This way, I can also define the variance function. Just like I have defined variance function, I have defined variance of a random variable, I can define the variance function of the process x, and for which I would need to know the density function of the process at all times, just like I did for the mean value function. Now, I did mention that we would need to find the joint probabilistic nature of two or more of these random variables. So the autocovariance function is just like we have the covariance of two random variables x and y. So if we have fixed values of s and t, I would have xs and xt as two random variables. So I could find the covariance of that, and if I knew the joint density function of x of t and x of s, I would be able to compute it. So that would be the autocovariance function. In particular, if s is equal to t, then the autocovariance function boils down to the variance function. I could just look at the product moment, so expectation of x s times xt, that would give what is known as the autocorrelation function. And the autocorrelation function and the autocovariance function are related in a simple manner, as you see on your screen. Stationarity. We did mention this word at the beginning of this section. So let's start this concept of stationarity by discussing the mean value function. So in general, the mean value of a process would change with time. So it's a function of time. Now, if it so happens that the mean value function is invariant under a time shift, so which means mu x of t and mu x of t plus r, it's the same. So which basically is saying that mu of x is not a function of time, it's a constant. So in that case, we would say that the process is mean value stationary. So this gives us the idea that we could have the process being covariance stationary, also known as second moment stationary or weakly stationary. In many cases, we just equate the word stationary and covariance stationary interchangeably. So a process is covariance stationary if the autocovariance function is invariant to the same time shift that we just mentioned. So the autocovariance function at s comma t, if it's the same as s plus r comma t plus r, then for any r, then the process would be covariance stationary. And in that case, or the autocorrelation function the same way, in that case, it's easy to show that the autocorrelation or the autocovariance function of a covariance stationary process is just a function of the lag. So it's a function of the difference between t and s. So we give a new symbol for the autocorrelation function of a covariance stationary process, and often it's r. So r xx tau is the autocorrelation function for the covariance stationary process at lag tau. Now, for a Gaussian process, whether it is covariance stationary or strictly stationary, it's the same thing. What is strictly stationary? Basically, if this property of being invariant to a shift in the time axis holds for any order of joint density or any order of joint moments, in that case we call it strictly stationary, which is obviously a very difficult condition to satisfy. For a Gaussian process, the two are equivalent, so that's another reason that the Gaussian process is so commonplace and so popular in the subject of stochastic processes.